In the next few minutes, I'll show you what pre-training really is. The trick that lets a model learn from raw internet text with no labels, the simple loss function at the heart of it, the data scale, the compute scale, the dollar scale, the moment a network of random numbers becomes something that looks like it's thinking, and what you actually get at the end. Pre-training is the most expensive single step in the AI pipeline, and once you see it, the rest of the stack stops being magic. Welcome to Concept Stack. We produce one concept a day, and each one stacks on the last, building the framework for AI together. Let's dive into pre-training. Last episode, we saw the transformer architecture. But an architecture is just a box. A fresh transformer is billions of random numbers wired together. It produces garbage. The question is, how do those random weights become weights that can answer questions, summarize documents, and write working code? The answer is pre-training. It's a single training process, run on the entire internet, that turns the random box into something we call a base model. By the end of this video, you'll know exactly what happens during that run. First, the data. Pre-training a serious model means feeding it most of the writable internet. The starting point is usually Common Crawl, which is a public scrape of the open web that adds up to petabytes of HTML. On top of that, you add books, scientific papers, Wikipedia, news archives, and code, every public GitHub repository, Stack Overflow, technical documentation. Frontier models in 2024 and 2025 train on 5 to 15 trillion tokens, give or take. That's roughly most of human writing in machine-readable form. The data is filtered hard for quality. Junk pages, duplicates, ad spam, machine-generated content, and toxic material are all filtered out. The remaining text is deduplicated, often weighted. Code is upweighted because it teaches reasoning. Scientific papers are upweighted because they teach precision, and chunked into batches. Data quality matters as much as data quantity. A model trained on a pile of low-quality text will be worse than one trained on a smaller pile of good text. But the scale is what matters most. The model has to see a lot. The genius of pre-training is that the task is absurdly simple. You take a chunk of text from the corpus, you hide the last token, you ask the model to predict it. That's it. The cat sat on and the model has to guess Matt. You compare the guess to the actual next token, you compute how wrong the guess was, and you nudge the weights in the direction that would have made it less wrong. Then you do it again and again, trillions of times, on every chunk of text in the entire training corpus. That repeat trillions of times part is where all the cost lives. How do you measure wrongness? With a function called cross-entropy loss. The model outputs a probability for every possible next token, and there are about 50,000 of them in a typical vocabulary. So the model is essentially saying, with this much confidence I think it's Matt, with this much confidence I think it's floor, with this much I think it's tree, and so on. You look up the probability the model assigned to the actual next token, and you compute negative log of that number. Confident and correct, the loss is near zero. Confident and wrong, the loss is huge. The model gets a strong signal exactly when it was overconfident in the wrong direction. Here's the thing that makes pre-training possible at all. There are no human labels. The old way of doing machine learning required armies of humans tagging examples. This is a cat, this is a dog, this is spam. Pre-training is self-supervised, which is a fancy way of saying the data labels itself. Every token in the corpus is automatically the correct answer for the tokens that came before it. You don't need humans, you just need text. And there's a lot of text. This is the only reason you can train on trillions of tokens. Paying humans to label trillions of tokens would cost more than the GDP of the planet. The actual loop has 5 steps. 1. Grab a batch of text chunks from the corpus. 2. Run them through the model, the forward pass, and have the model predict every next token. 3. Compute the loss using cross-entropy. 4. Do the backward pass, which is calculus that figures out for every single weight in the model whether nudging it up or down would have reduced the loss. This is gradient descent. The gradient is just a list, one number per weight, saying which direction to push. 5. Actually nudge every weight in that direction by a small amount, called the learning rate. Then back to step 1. This loop runs roughly 100 trillion times for a frontier model, parallelized across thousands of GPUs working in lockstep for weeks or months. Every iteration moves the model an imperceptibly small step toward better predictions. Over enough iterations, imperceptible compounds into transformative. There are 3 knobs you can turn during pre-training: parameters, how big the model is; tokens, how much text it sees; and compute, how much raw GPU time you throw at it. Whole field of research called scaling laws studies how these 3 trade off. The most famous result, called the chinchilla rule, says you want roughly 20 training tokens per model parameter for compute optimal training. But the headline is bigger: scale all 3 together, and model capability goes up predictably. Doubling the compute reliably improves benchmarks by a measurable amount. There has been no plateau yet. Pre-training is where the money goes. GPT-4's training run is widely estimated to have cost between $60 and $100 million. Frontier models trained in 2025 are running at $200 million to over $1 billion per training run. The bulk of that is GPU rental. An H100, which is the current workhorse, rents at roughly $2 to $4 an hour, and you need 10,000 or more of them running for weeks. The energy alone for a single run can match the yearly electricity consumption of a small town. This is why only a handful of companies in the world can afford to pre-train a frontier model. Here's the surprising thing. After spending $100 million in a month of compute, what you get out the other end is not ChatGPT. It's something called a base model. The base model is brilliant at one thing: extending text in plausible ways. Show it a paragraph, and it'll continue it convincingly. Show it the start of a programming problem, and it'll complete the solution. Show it a poem, and it'll keep writing in the same meter. But if you ask it a question, it might just write more questions, because in its training data, questions are often followed by more questions. It has no concept of being asked something or expected to answer. It doesn't refuse harmful requests. It doesn't stay on task. It can drift mid-paragraph into the style of whatever it thinks would naturally follow. The base model is the raw material, incredibly capable but unshaped. The chatbot you talk to comes from a second, much smaller training step we'll cover next time. Step back for a second and notice how strange this is. The training task is just guess the next token. But to guess the next token well, the model has to internalize grammar, world knowledge, arithmetic, logic, code structure, scientific reasoning, and a rough model of what a paragraph is supposed to mean. Predicting text correctly across the whole internet turns out to require a working model of the world the text describes. That property is called emergence. The capabilities emerge from the simple task. Nobody built reasoning into the model directly. The model built it because reasoning was the cheapest way to predict tokens. That's the magic. That's the end of this concept. But each video stacks on the last. Subscribe, and we add the next layer tomorrow. So that's pre-training. Trillions of tokens, a self-supervised next token prediction task, a single loss function, and a $100 million compute run that turns random weights into something that can complete text in startlingly intelligent ways. But what you have at the end is a base model. Brilliant at completion, bad at conversation. Tomorrow we close that gap, fine-tuning, the much smaller second training pass, plus reinforcement learning from human feedback that takes the raw base model and shapes it into the assistant you actually talk to. Thanks for watching.